Hello, everyone, and welcome to today's live stream. Well, I have no idea what we are going to talk about today, but let's figure this out. Right. Uh, where is it? All right. So let me walk through the last 2 weeks. So the last 2 weeks we did. The first week we did understanding the high level goal of the project and why non-stationary worlds matter for AGI. See how the environment, predictor, controller, and metastack fit together. Metastack is just a stack of meta learning processes that we have built in the system, and know how ARC. I think we talked about ARC, price, and AGI, and then cellular automata as the main goal, as the main test bed for this model we're working on. So we will build, I think, in a few weeks, maybe two, maybe one, but in a few, sometime in 2 weeks, let's say 2 weeks, we will build a cellular automata where we'll run some tests on it. I mean, we'll run the environment in a CA kind of nature, then have a clear roadmap for, we did this, we metrics first, baseline predictor, we found adaptive rules, meta ecosystem, outer evolution. We haven't touched multimod models. Adaptive rules are adaptation rules. I haven't shown you. Well, I showed you, but I haven't shown you how to actually adapt the rules using evolution methods and memetics and autopilot and meta tuner all fall under this. Equilibrium also fall under this, where the system does its own like controls or uh, co- uh, um, changes based on the environment, event based. So if the environment changes, the system also does change. And then we can also talk about the evolution later on. So the evolution is just we evolve a system, we evolve the rules, usually just the rules, and see how when you use the evolved rules, by evolved I mean rules that are I call them best genome. So if I evolve a rule and I find the best rule possible or the best genome of the evolution, then I use that in our code. So for example, we have this plug where it controls the best genome. So I think I talked about this, but that would be I haven't shown you how the evolution work. We will do some simple evolution later. And now those are week one, what we went through. And then week two, we did some debugging, the recursive least squared. This is the algorithm for online learning, but like the system learns online or as it goes. So this is what we did debug, and we found that a few things that needs to be changed, need to be updated for this to really work, because it works, but doesn't really work as we are supposed as we want it to, because it works in an environment that is not changing at all. Like we don't we don't make changes to the model or to the environment. The model is just uh, what's the word? It's let me show you I think I showed you what these plugs are. but it should be bandit something. Yeah, so this is off. Now what this does is it just allows RLS to do learning online. And then every time the system changes, we use that to update the model. So if a system changes and then the model recognizes that the system has changed, it has to update its parameter to adjust to adapt in a sense. And then we do that. We turned it off because it was when you turn this on, it's making the model forget a lot. And part of the reason we found that when you have a higher learning rate, so we had a 0.08 here, but now it's we reduce it to just zero point 0.1, 0.01. And then the order was 3, but 3 because we didn't have the actual, we didn't match the order plus what the code was using. Because in the code we passed, I think two orders, two sensations. I think let me find that predict.update. So we only well we just have previous x and previous x previous to. Oh, this yeah. So x previous to and x previous, which means that previous two, previous one. We only have two, but here we will have three. So we changed that, solved the problem. We also reduced the projection dimensions from 64 to 24 to 32. That also solved the problem. But now the major thing is um, why should we turn this off? Like it works, but I'll say it's a model that without this, the model doesn't really do anything interesting. You expect something to a good model to be in. So a good model is a model that trains, adapts, or does a changing its parameter when it learns. Now what we found is this when this is on, the model does forget a lot because one, let me just show you where this is. Go to equilibrium. Yeah, so this, when it's enabled, you see we are applying predictor order, and this predictor order is what we are doing. What does the update? So we are resetting the dimensions. We are setting the model to 0, like we are telling the model to start over again, like it loses the entire history it has been learning, and uh, so only previous x and previous x2. So it sets that to 0, which means the model forgets everything else it has learned and starts from scratch. Now, how do we keep this on and still make the model still, do better? One thing we found was let me just open these. Was it? I think let me get. Also, let me just walk through this. So we also found event modulated plasticity. So what this is so if we go here, search for these. So we read a bit about this, but it's really just AI terms because this was something we got from LLM. But in real sense, what it means is just uh, plus like neuroplasticity. Like if you familiar with neuroplasticity, what this tells is just controls how like neurons learn through this process of controlling the strength between different two neurons, how strong they are connected to each other, and that's just plasticity of the brain. But since we are using an we are training something different from the actual human brain. We want to figure out how to actually do that. And this controls learning. So if the strength of two neurons is is high, is it high or it's powerful or strong, then we are calling that we are we are saying that, if that's the case, then the learning and memory is becomes something um, like becomes a brain or a way the system keeps learning better or keeping the memories that matter to the system. Like memory becomes okay, and learning also improves when the strength of the neurons or synapses is strengthened through different mechanism. But that's just neuroscience. And what we want to figure out is how do you modulate that? How do you use that? How do you use the events that already exist in the system to control how the system learns? And from the code, from our code, we have something like this. We already have, changing the system, changing the parameters based on the selected arm state. First of all, you pass the state of the current system, and the state we are getting this state from the adapted or the equilibrium. This guy. So this is like the entire state of the system at that specific step. Now, what we want is how do we um, how do we figure out how to uh, control plasticity based on the events, based on the system's current state? And yeah, so the description is pretty clear, like neuronal or synaptic plasticity that are influenced by specific events or contextual signal. And in this case, we have the state. So if we pass in the state, it gets that state and uses that to get, if they are not really equal, then we change the updates. And then um, we also found out of other things that, so we went through this. We did not go through the coding process. We just went to the theory, figured out what it is, and read a bit about this. And then we had a few suggestions from GPT where we have to, if we want the model to really learn as it goes, we can introduce this thing called plasticity gating, where gating is just keep having gatekeeper or something like something that controls how the system changes and when it should change. So when and why and where. I think when and why it should change. So we don't just change the system as we please. Like the system should know when it should change and why it should change and how actually. So this is neuroplasticity, and I think it relates to this idea of neuroplasticity and amazing ability to reorganize itself by forming new neural connections and pathways throughout life, allowing it to adapt, learn new skills, habits, recover. So neuroplasticity relates to this concept. But how do we do that? Like sounds it sounds complex. It sounds easy. No, I mean, in theory it works. Like you can talk about these things in theory. You can talk about neuroplasticity and feel it maybe if you can. But how do you program this thing? I don't think it's an easy task, and that's why we want to explore how, like, what mechanism we can use to do this, to do some getting. as a way to do research, not to build something that does actually this. Because as far as AI is concerned, as far as building uh, systems that learn and do interesting things is concerned, we can try, but we can't really. There's some sort of verification process that has to go through. This has to go through so to verify that it actually works. But if we can do research, we can, see how different mechanism or different parameters can influence the system. And we learned also a few other parameters like pi prediction predictors learning rate and how it influences the system. And that's here. I think that's this guy. So we have the learning rate as zero point 0.01. So zero point 0.01 is a better learning rate, and we will use that throughout the system because we found that it's good. And then read about this. Now, this week, which is week 3, I think, week 3, what we will take away, maybe what we will be looking at. Um, let's see, what's this? Where the hell is that thing? There you are. Okay, so what? First, we want to know how, why, what? Okay, we have plasticity gating. Um, how do we actually do this? Plasticity gating in our current model. So okay, the project is called Loopseed, so I think probably there's a better name for this, but yeah. So how do we do this? So that's what we will find out in this week, and probably learn more about this neuroplasticity, and we can also probably try to fix whatever. Okay, so the results, let me just walk you through some results and save these first. So the previous results, uh, just, I don't know, was it 34 or the last run was, hopefully it was 34. 45. Jesus Christ. What's this? This is not. Okay, let's see 45. 45 is not, it's not the right one. Which one was this? Now I have to know which the last results. Yeah, let's just run another one. 46. Don't want to see source. No, 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 no. Sourcing the wrong thing. Okay, so Python run for 20 steps, 20,000 steps, and ensure everything is set up correctly. This is stand. Predictor is okay. This is fine. This is fine. Okay, great. Let's do this. I will just leave it to run for these many steps, and hopefully it doesn't blow up. But yeah, so this is what we want to explore today. First, we want to see the results, why we want to use plasticity. And remember, I haven't turned this on, so it's still off. So that means that the system is not, it's static. It's not using any. The only change it uses is what we are calling dynamics. So the dynamics state, is it dynamics. So this is the only change we are give the system is using. So we are only changing A, which is the dynamics parameter. So A is the observed state, the current observed state, and then this is actually C is the observed state, and then this is the actual state, which is based on these 256 state dimensions. And then the observed state, which is 128, is based on C. So C is based on that, so the readout. So that's only the thing that is changing now. But that doesn't change. It doesn't change the RLS. It only changes what the environment, what the model sees, or what um, our model sees. So what we will do, 46 is okay, and I'll just try to let me get this out of the way. And 46. Okay, okay. This system is doing fine, but wait, what? This is different, but we don't. Coherence is still doing okay. This is different. So all right, so medium, mean, and median is fine. Okay, so this is fine. This is working. Wait, how many steps are we? 13. Wait, let's wait for it to finish though. Okay, so once that is done, I'll show you the good results, and then we will turn this on, and I'll show you the bad results. The bad results is when the system forgets a lot, when this is turned on. And when this is turned on, what is happening is, so this is where we'll start actually to do debugging. So we'll start off with this, figure out. So the order is, what is the order? Period, bandit order periods. Bandit predicts. Okay, so this should be. I see. So this is, we have two here, and this should be two because order is two. Okay, we can get rid of one of it, which is four, and then period. So this is changing every 3 steps. That's fast. Like every 3 steps, you change the environment. That's bad. We can try every 1,000 steps, or every, so 1,000 is too high, but we can do 200 or 100 in the next run. So this is okay. This is finished. Let's see the results. So the results is okay because we are not we haven't turned we haven't turned this on. Bandit is not on. So we turn this on, and we will see that some changes. So let's make this 47 so we see the results. So when this is on, um, okay, when this is on, we have bandit enabled. Then we have self dot bandit orders, which is this value, these values. It's a list of two values, and then state dot bandit total model period. So every 3 steps, every 3 period, which is this, we create a new arm A new army just means a new state, a new state, and then a new state for the model. And then if it's not equal, we update it. Now that's doing it every two steps, and the apply predictor is doing the same what I just explained to you. So we will try this run for another 20,000 steps, and we will see when it fails. It will fail at some point. And let me see. It should be 40 what? 47, yeah, 47. Hmm. Okay. Now it's training. Does that for a couple of 2,000 steps. Goes to 88. Yeah, it's a lot of going on here. Okay, so it actually failed at the which step is this? It failed at exactly 3,640. So this is where it failed. It went to zero, directly to zero. That's because we have this on. The bandit is on. This apply predictor order it's working. It's active. Now we want to explore ways to solve this. So we can start by maybe increase because three is a lot. It's fast. It's changing every time. Like that's fast. We can make it 200 or let's try 100. Or actually, let's make it 50 first. And so this never it never gets it's always bad steps, and then pi is also up there. Now let's cancel this and try uh, making so many of these. 47. We will use 47 for now. No way, no way. I can't delete modified voice. Is off. Okay. So I think I'll do it from data runs multi gen 47 and run these again. So we have a now the model changes every 50 steps. Let's see how it does. But ideally it will do well, but still it will I think it will perform bad when you make it run for many steps. So I think doesn't help. Changing this order period is not helping. It won't help, but let's find out. Okay. So the previous one was 3640. It failed at 3640. And this one we will check it. So let's keep this. So 3640, it went down to zero and then stuck there. Did this. And this we want to go to check for when does it fail. It's still okay. 30, yeah, it passed the step. We are 45, 47, still doing great. In fact, it gets better. it's stuck up there. So changing the model every 3 steps was pretty bad. But yeah, it failed actually. So we at around 60, 65, 60, the model goes to zero. See that from the graph there. So this is it. This is the magic. Goes to zero at this step. So increasing the step just pushes the problem into the future. So it will appear in the future at some point. Now, so how we want to explore how which actually. So this might be the issue here. We're setting everything to zero. What is the best way to do this? Should we reset it? Because if we reset everything to zero, it just tells the system, forget everything else. All right, so let's see. Making this to, let's try 200, because let's try 200, see how it does. And then we can try to figure out how to solve this thing here. Just keeps at zero, never changes. Let's stop this and remove run. So we are changing it every 200 steps, and every 200 steps we change the model. Every 200 steps, um, apply the change. Okay, so if this is changing it to zero, why should we update the model with zero? Maybe we can use the observations. What this is the observed, the sensors. If the sensors change, now that's when we change this model. I think so. Because this is so the observed is x. X is now return. Dimensions. Okay. If observed dimension is not equal to the x previous dot size, and I can do this. If observed dimension is not equal to frame 2, can do this. It says what x is not defined. X what do you mean? X previous, oh, it's system dot. Can see what this is. I haven't saved, but for now. And oh, okay, what happened? When did it happen? This is even so fast. Happened. This happened so early in time. Oh my God, it went down so fast. Anyway, so we know we can't really rely on, let's try 100, but we can't really rely on period. But it's important that the period does it, it's not too small, has to be a larger value. Okay, so we try 100. And okay, so the one that fails early is 200. Let's keep that and check for, try to test this code. But let's see what is the what is this print observed dimensions and x priv dot size. System dot priv. Then we want to stop this. There'll be a lot of prints, but we only interested in after every 200 steps. There. What? Touch. Our dimension is the same. Okay. And it's Boolean value of tensor with a more than one value is ambiguous. Okay, so we know that the size is, what about the other one? So also print this. Preview 2 should be the same. Let's fix this bug first. Tensor. Oh wait, what? No way. Oh, size. Oh, okay, so this it should be size. Use size dot. Okay, it's 21, 28, 128. Okay. What? It's still the same. I don't understand. Oh, I see. So this should be dot size. It's it's still the same. I don't think it changes. Yeah, it's still the same. It's fine. Let's see if it changes some point. No, I don't think it will ever change. Wait a minute. Maybe we are comparing the size instead of the values. Oh, oh, it should be observed, not dimensions. And we can get rid of this. So check these. So the observed and the actual x prev 2. Cancel this. Okay, let's find out what this is. Okay, there you are. So this is what? This is not even close to being the same, is it? Oh, it's the same. No, it's not the same. Okay, it's not the same. Looks the same. It should be. It should be the. Let's compare if they are the same. I'll print this observe equals to some xp, and this observed equals to system.xprev 2. Okay, cancel, remove Python. Okay, let's see if there's any difference, because we want to detect the difference. If there is a difference, okay, if there is a difference, then that's when we change the system. Oh, this says these are equal. This is oh, I need to know which one is this. So let me print this as it's confusing to read. Let's just print this x prev and this to be x prev 2. What's happening here? Okay. Let's see. So the first one, xprev same. These are the values, and then this is the second one. Xprev 2 is not the same as the observed. Okay, so if xprev, okay, which one is always not the same? So xprev 1 same, xprev 2 it's not the same, xprev 1 same, xprev 2 is not the same. I think we are comparing the wrong values for xprev 2. Xprev 2, xprev 2, which one should we compare with xprev 2? Observed array. Observation array. Tensor clones. Order is 2. Update that. Observe. This is the. I'm comparing the current sense, and so this is the current sense, current step, and then x prev is previous step. X prev 2 it's 2 previous steps, and it's guaranteed that the current step will, well, it's equal to the previous step. It's false. It's always true. Maybe that these two values are equal. X previous sense current senses are equal. Strange. Let me find this. Why is this happening? Because system is we got to the kernel. Small. Predict dot updates. So we have previous x. Previous x is the previous x, and then since x, and previous since x. Go to predictor. Go to updates. By x1 and x2. All right. Where this is x sense x, system sense x. This is the observed current step, and system dot previous. It's the previous observed x, and system dot x prev is 2 steps back. So there, this should be. This is expected. It should be false. And this is all true. If this is true, then it means that we will only be changing x2, previous x2. All right, this is not right. Okay, let's see. Observation, unless I need to change something else. So the observed is this, and it's to tensor dimensions. Because if I use the dimensions, it's always the same. So I don't think that's the correct one to use. If we use the actual senses, that makes sense. But why is it the same? System previous observed. So observed senses. So somewhere sense dot x is sense. Oh shit, I'm in the wrong. Okay, this sense x sense x. Hmm. Okay, sensorium. Types. So this is x array like. This is not right. Should not be 2, but I think observed dims. Okay. So, Zeros. Okay. Zeros. Zeros. Hmm. What's zeros? Zeros is a tensor. It's just using the dimensions to make zeros. Okay. Subtractive dimensions zeros. I think we can try this. Okay, let's see. It's already done. And it's still bad. Oh no, I think I need to run this again. This only changes. Oh shit. What is that? What intense is ambiguous. Is that right? Ambiguous. Oh, which one is this? With the more than one value. Observation. Okay. Mm. Should we reset before checking or reset dimension? Oh, wait. Should we reset predictor? Okay. Really? What's happening? Oh. Oh, okay. So this is I don't know. Reset dimensions. What? Never gets there. It only gets there for the x2. Maybe X2 is the one failing. But anyways, let's find out. Still doing okay, still okay, still okay. Last one failed at around this step. 2000. Wait, this is 2000 or step is this? Around 4000. We are at 3000. So gone. 4000. Still okay. Still doing great. Still doing great. Still okay. 34%, 35%. Any charts? Uh, Neeraj, can you explain this a bit? Looks challenging. Which part? Sorry, Neeraj, I think I can explain whichever part you want me to explain. Well, the idea is we're trying to build a model, a predictive, adaptive predictive model, and the goal is to have this model train in a different in an environment that is chaotic, or if you like, an environment that changes all the time. Let me just give you if you're new, actually, I think I explained this in my previous live stream, but this is the end goal. I mean, if we can have a model or a system that you know tries or tries to solve this arc price. And the goal of the arc price is to test how well AI models do what perform well, or how do they perform in uh, such problems that usually humans are good at. And what we are building here is we have a system already that um, we have a system already, and this system is using a lot of plugins, meta learning, and a lot of adaptive methodologies. We're also using evolution and also memetics. So memetics is an example of a cultural nature in a system. So if we have different agents, let me show you an example. If you have is this yeah, if we have different agents, we have agent 0, agent 1, and agent 2. We train them in the same environment and see how they perform differently. If they perform the same, or if they perform differently. And then we have configuration files. So configuration files is what the system uses to we can call them rules, the rules of the system. We give it the rules, and some of the rules are handwritten, and the others are we run an algorithm to evolve them. For example, this genome, we run an algorithm, we evolve the rules and find the best genome for training, and then we use that genome in our config for allowing the system to train, to do better, to analyze the system. And then after that, once we have a system that trains better, and we see by better, I mean we see the results right here. So the graphs tells us how the system is performing well, and all that good stuff. And I think that's just summarize everything that we're doing here. And once we have a system that does well in any environment, so the environment we are testing it on currently is this, we call it richer. So richer is the current environment we are testing this system on. So this is a two dimension 2 by 2, I mean sorry 2 by 2 2 dimension environment. We run the system in this environment and see, because richer is almost real in AI world, so it's an almost real world or box. So it's 3D 2D box, and then we train that model inside that, and I can show you what that is. So we have two environments. We have richer and toy. Toy version is just, toy. You just write your own is it data and then train that on. And then richer is the one that's the almost real one, where we train this model on and see how it does. And by chaotic is richer is a chaotic environment. It's almost real, so the environment switches, changes. I can see an example of this picture, like a robot is trying to, walk in this environment. Now the goal is, if we can have an adaptive controller or adaptive predictor, then that will be like a system or the brain of a robot, and that will control the robot in such environments. And that's what we're trying to build, and we're doing this using as many things as possible. If we can do we are testing it on this environment. We are using RLS, online running. So RLS is what we are currently trying to figure out how to fix it. And then, yeah, and if you're interested in like knowing what exactly we are doing, is you can go to my previous live streams. I can, find them. I can try to find them and yeah, point them right here so that you can find them easy. And these are them easy. This will be this will be and every week we'll do this every week. Every time we have something to talk about, but it's sequential. So every stream leads to another stream. Like the previous stream, we talked about plasticity, and now we are trying to figure out how to code that in the system. But to do that, we need to first of all figure solve this problem where changing, like we rewrite the entire system, which is like the system lose the history of memory, like all the memory that it has been learning, it loses it all because of like what the how we have coded it up. So yeah, so that's the whole thing we're trying to do here. But if you get lost, think there are previous streams that have explained the entire process, everything, parameters, and the configurations, the end goal of the project, and also the bugs and the features, everything. But let's continue. So this is the last run. So the last run it should be bad. Like expected results should be bad. This is how many steps? 20,000 steps. So this fails at around these steps. These are 7,400. That's not good. But I guess I know why, because one thing is we are checking X previous and X previous true. These are the same. X previous and the observed current observed value and the previous observed value. So we had previous observed value, and that's just the senses of the what the system sees, and that's in this tensor. Oh, I can't see that now. But let me print this so we see the difference. So we found that it's almost so it's always the same for current observed and the x previous system dot x prev. So that's always the same. What's different is if you compare the current observed and then and previous system dot x prev two you go two steps backwards. You compare that and the current one, they are different. That's expected. What I'm not sure about is why always x prev is two previous one previous step is the same as the current observation. I can try to x prev this, print this. System dot x prev. Right, so hopefully it works. Okay, so this is, let me stop this. So this is what we are, this is the observation we're seeing. It's a tensor. Okay, so this printed before. I'm printing observed and x. Okay, observed is this. No way, why am I doing it double? Okay, so this is the observed. The previous step, the previous one step is this. And that's we're finding this is the same as the observed, and the observed is just x what since x. All right, let's see. Let's run this. Okay, so this is what is this? Why is it two? No shit, this is two. Remove this. Okay, this is fine. So this is the observed, the current step observation, and this looks the same as the previous step observation. In this case, I think I don't know why it must be something wrong with this because it's exactly the same. Also, this is x prev two steps. X prev two steps is also the same. No? What? The same as the observed. That is strange. In short, these values are all the same. And this is observed, previous, and x previous to, x previous, and x previous to. They're all the same. Something is not right. Reset dimensions. Okay, let's go here. The state, the current state. And find out about sense self dot sense of x. There you are. So I'm updating x here. So this is so x observation. I'm updating it here. So every step equilibrium. So equilibrium. It's not here. Oh no. It's not even here. Oh, it's not even called that. So I think I need to call it something else. Online genome manager. Init function. I'm running a single run. Single run. The x value is not. It's not actually. It's not working. It's not the right value we have. We are passing to this. So config. Get the config, which is everything, like the entire thing. Get equilibrium. Config path. Equilibrium values. Is this after the system or before the system? This is after the system. I see, okay. So we update every time the system updates. Compute energy, energy is fine. Update state. Okay. Where see apply. I don't know why this is always the same. System. So system is it updated? Maybe the system has not updated the state yet by the time we get here. But it should be system.state observe. So single run. So observe single agent agent ID. The system is fine. Every step we get the system, the metrics of the system. Okay. Let's see questions. Yes, that's correct. So we're trying to build a dynamic system which learns in real time. Yeah, and the learning in real time is what we are trying to figure out currently, because what we have is we have plugs, and those plugs helps in controlling how the system learns. And in real-time learning, we are using this uh, algorithm called recursive least squared. So recursive least square is just an adaptive algorithm uh, for learning in real time, online learning for adaptive systems. And so the bug is actually that the system is always it when we turn RLS on, the system fails or doesn't learn as it's supposed to be, and we can see that from coherence. Coherence is just how accurate the system is doing, how learning process control check measures the learning process of the system. And we can see that coherence is pretty bad right here. The mean is 0.38 or 34. Oh, sorry, point 4. Jesus Christ. Okay, so it's pretty bad. Training is bad, and the median is point zero 0.01. So this, whenever we turn the system on or RLS learning on, the system forgets a lot. It doesn't keep memory. It doesn't learn so well. And the learning so well is simply because of the this phenomena we're trying to solve. That is that it forgets, it rewrites the entire history to zero. So, and that's seen in this code where the predictor updates everything that the system has learned to zero. Now we want to control that, but controlling this doesn't actually mean that the system will learn better. What it means is that we have just muted the phenomena, and we want to um, the research that we're doing currently is we want to figure out how to code this idea of neuroplasticity, and neuroplasticity is just getting the system um, to do reorganization or to learn based on events, based on what it actually sees, right? That's what we are trying to figure out. Yes, so it's a dynamic system which learns in real time. Are you a researcher? You're working alone? Well, yeah, I am a researcher, and mostly this research project is just to build something that adaptively learn, and it's not it's not under any organization. It's under um, Dialect Technologies, where we build AI systems. And the first we don't build AI system like just AI system. We build many products at Dialect Technology. And one of the projects that we are working on is this adaptive predictor or controller. And this project is it's really to just test how well systems, or do research in how well systems can learn well and can adapt well and use energy well. So we have introduced this free energy principle, the idea that energy is a huge thing for AI systems, and free energy principle it's an idea we are exploring, and we can see from our system is energy is a factor or a parameter that um, so for example, this controls the budget and how the system uses energy. If it shoots, then we know it uses more energy. But from this, we see that energy doesn't overshoot except a few steps here. So energy is still okay. So the system is using energy okay, right? But these are some of the ideas we're exploring, free energy principle, and we're also exploring this strange loop idea, and it's a referential, self-referential systems. So the idea of strange loops is mostly people who work in consciousness or AI consciousness have come across this idea. And incompleteness theory is also another idea we will explore throughout this research. But the whole point is to the community to engage, to throw out ideas and solve try to solve it on this stream. And yes, and for for research, I'm an affiliate research at Wolfram Institute, so that's really just um, place I do uh, my thing, my research, where I research in complex systems, AI, and consciousness mostly. And then I also do computational systems like Turing machines, cellular automata, and explore how these systems can be used to understand most of the things we do, from brain science to biology, which is also just part of brain science. And yes, so that's just yeah. Are you a researcher? So that's the answer. And is there any documentation I could read to understand everything? Okay, so I can create so that's a good idea. So I can like document this. I haven't really documented this. I thought maybe documenting it through streams is a good idea so people can, watch the streams. But if it's required, if you want a documentation, I can craft it and then uh share share with you. You can, email me, send your email something on the chat, or let's see, maybe yeah. But yeah, I'll create a document, and then that document I'll attach in every stream, so you can find it. Actually, I'll attach it in this stream so you can find it easily. And no other questions. I think that answers the questions. But yes, so we are um, we are here. We still haven't figured out how to make this train in real time. So RLS is something we are trying to explore. And yeah, if we get this to train in real time, and so just to show the best results that we have, um, that is doing well when it's not using RLS. So this is the best results we have. Coherent is 0.99. It's doing great, and this is because we turned RLS off, so there's no sort of real-time learning, no updates, no nothing. It's doing great. And but when you turn this off, the RLS on, this is the behavior we have. The model, I think I have old, must have, okay, must have updated this. But yeah, it fails. It does really bad, and that's what we want to figure out, to find out, and solve it. And once we have a model that can train in real time, our goal is to build a cellular automata, and cellular automata will be our test bed for this model. So if we have a CA, that CA can, we can run this model in a CA kind of environment. And so if you know this idea of game of life, the game of life, you supply rules to assist to a cellular automata or just a CA that uses some sort of rules. Usually is just um, left, right, like within the surrounding of a point. So we use those rules, the update rules, and so you run the system, and depending on how many steps you run it, you find this behavior. Oh, it's called Conway Game of Life, like gliders and interesting things happening. But so what we want is if we have a CA and CA have some sort of target and the initial conditions, which are the rules. We supply those rules to our model, and the model learns those rules and then tries to, make predictions, adapt the rules so that it fits the target or it finds it gets to the target. So assuming you have something like this, you want the model to predict this being the target. You want the model to come to predict this. Of course, you can write an algorithm to do that, but um, what if you had a model that reasons, that uses symbolic reasoning to get this structure? That's what we're trying to build, and go same thing. Yeah. So at the end of these streams, you can either go when you have learned something, or you've learned about um, what is interesting to do, what we can do next, the next week or stream. Okay, so that's the end goal. Yes, so yeah, game of life. That's the thing we are. Yeah, exactly. So what do you think about emergence? Thank you. So emergence is one of the things we would be looking at. Like we want to pay attention to at what we call emergence behavior. So you have a system, and you run this system for a certain amount of steps or a certain amount of time. And depending on the rules or depending on how the system is constructed, some sort of things might emerge, some behavior. Like in the game of life, gliders are some of the phenomena that emerge in the system. Now, that's emergence, and this is something that emerges out of nowhere. It's not programmed, or it's not pre put into the system that you should do this. You just run the system, and then some behavior emerges. And we see this in life, and we see this um, biology and physics. Emergence is part of the story there. And yes, so I don't know. Uh, on this project, I have explained everything. And on this, if you want to know about everything that I do, you can can check out my site, and there's some things you can find from this. This is just me, but on the project, this is what we want. Emergence is what we'll be looking at most of the time. Some of the time, we will look at emergence, see if in fact, we thought initially in the stream, we thought this was an emergent behavior actually. So when we ran this system for a few steps, we thought it's an emergent behavior, and um, yeah, and maybe it's not, maybe it is, but I think it's just a bug. So let's just fix that. Then we can talk about emergence. But once we get this bug, the model learning in real time, I think that'll be a win for us. Then we can explore other things like evolution, mimetic culture. We can run different agents and see how they train in the same environment. But yes, I think we are out of time, so we can stop there. If you have any questions, you can reach out to my email. Let me see which email I can get in touch. Yeah, I think let's see. Comments, talk, ask questions in the comments, and thank you for participating. For everyone who participated live, thank you. And I think we can meet next stream, which I don't know, tomorrow maybe. Yes. So thank you so much. See you in the next stream.